Okay, Algebra 2, this is section 7.4, graphing rational functions. We started this section yesterday, and what makes this different from section 7.3 was in section 7.3 we had equations like 3 over, let's say, x plus 2. And I know that 1 over x looks like this, but the x plus 2 is going to move him 2 units to the left. So 1, 2, 2 units to the left. And the 3 is just going to stretch him out just a little bit, so he's going to be like this instead. Okay. Now, in 7.4, we have functions that have x's on both the top and the bottom. Top and the bottom, top and the bottom. Okay. And I said when you're trying to find your vertical asymptote and horizontal asymptote, you do these steps. So for vertical asymptote, you set the denominator equal to 0. So in example 1, down here, we ended this yesterday. In example 1, we set the denominator x minus 1 equal to 0, and we add 1 to both sides, so my vertical asymptote is at positive 1. We went ahead and drew that in there, okay? And then I said the rules for horizontal asymptote, there were 3 of them, and they have to do with n and m. N is the degree of the numerator, and n is the degree of the numerator, and m is the degree of the denominator. So down here, my numerator is x to the third power, so it has a degree of 3. And my denominator is x to the first power, so it has a degree of 1. So n is 3, m is 1, and then I compare them. So if n is less than m, y equals 0 is my horizontal asymptote. If n equals m, we'll talk about what this guy means today. And then if n is greater than m, there is no horizontal asymptote. So here I have n is greater than m, so I have no horizontal asymptote. That goes with rule number 3. All right, so there is no horizontal asymptote here. And then I told you guys to go ahead and plug these numbers in for x here. So like taking negative 3 to the third power over negative 3 minus 1, and doing the same with negative 2, negative 1, 0, blah, 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 all that stuff. These first 4 numbers in the table are 6.75, 2.66, 0.5, and 0. Okay, I'm going to go ahead and plot these points on here, and you do the same, and then I'll show you what this guy looks like when you graph him. So if you need to pause this video to graph these, go ahead and do so. All right, so on this graph, here's where all my dots are, and I have no idea what this thing looks like. Well, I do actually, but it's since I have my vertical asymptote going through here, it kind of takes a funny shape. This is a weird one. They did this as a separate example because it doesn't look quite like any one of these 3. Usually, if you have a vertical asymptote and a horizontal asymptote, it looks like this. If you have 2 verticals and 1 horizontal, it looks like this with a parabola in the middle. And then if you have 1 vertical and no horizontal, it looks something like this. But this one is altogether different. This one, if you graph him, looks something like this. Okay. Typically, when you have a vertical asymptote that goes up and down, you have a line that's going to pinch in towards him and go on forever and ever and ever in one direction. This one's going to kind of do the same thing, but he's going to be like he's going to go straight up that way, and he's going to go straight out. So this one kind of looks a little weird. You've got one going forever and ever and ever down, and one going forever and ever and ever up. Okay? If we would do domain and range on this guy, domain, range. Domain is left and right. He's going to forever and ever and ever go to the right, and he's going to forever and ever and ever go to the left because of these 2 guys. But he will not ever touch this middle line. So x will not be equal to 1. Okay, whenever you have your vertical asymptote at 1, that means your domain is x cannot be equal to 1. For your range are your y values going up and down. And it doesn't matter that we have 2 of these. I just know that this one is going to touch every single y coordinate. Okay, because he's going to go forever and ever and ever up and down. So this one has all rails for the range. So kind of different. You won't have too many of those that look that funny, but that's why they give this as an example. So, all right, flipping to the back side. Example 2, we have a real life function here. and they're talking about a boat. So a boat is traveling upstream at R miles per hour, and then during the return trip, the boat is traveling at R2 miles per hour. The average speed for the entire trip is given by this equation. Okay, so let's say that since I'm going upstream, let's say my first, my first miles per hour is 40, and let's say my second miles per hour is 50. My return trip, I'm going a little bit faster. Okay, so to use this equation, just to demonstrate, to find my entire speed, I would take 2 times 40 times 50 divided by 40 plus 50. And that is 40 times 50 is 2,000. No, 20,000. 20,000 times 4 is 40,000. 40,000 divided by 90, and that comes out to something like 44.4 miles per hour. So approximately 44.4 miles per hour is my speed going for each one of those. Okay, but then they say, well, let's say that R1 is going to be your independent variable, and I know that R2 is 10 miles per hour. Okay, so they want me to plug this R2 into the equation up here. So I've got 2R1 times R2, which is 10, over R1 plus 10. All right, this simplifies. If I take the 2 times the 10, that's 20 R1 over R1 plus 10. Okay, now this is kind of like saying y equals 20x over x plus 10. Normally I would think that, like, well, let's just do, if I have a vertical asymptote, I set the denominator equal to 0 to find my vertical asymptote. So x plus 10 equals 0 and x equals negative 10. So my vertical asymptote here is at negative 10. You can kind of see that from the graph. And then to find the horizontal asymptote, we look at n and m. So n is the degree of the numerator. It's x to the first power, so n is 1. And m is the degree of the denominator, x to the first power, m is 1. So here is the scenario where I have n and m being both the same. So I'm going to flip back to my rules. The rules are here. If n is the same as m, I look at leading coefficient over leading coefficient. So this is that second rule, that middle rule. Y equals, and if I look at the leading coefficient means the number out in front of the whole thing. So I have 20 here, and there's no number out in front of x, so I just assume that it's 1. So y equals 20 over 1, or just 20. That's my horizontal asymptote, and you can kind of see that that's here at 20. That's where their dotted line is. And then they've got their parabolas going like that. Okay. What is the domain and range of the values in the context? So domain and range. The domain is the set of x's going left and right. Since the vertical asymptote is negative 10, x cannot be negative 10. And for range, I look at my horizontal asymptote. So since y equals 20 is my horizontal asymptote, y cannot be equal to 20. So that's kind of how that works. Okay, so there I had an n and m that were the same, and my horizontal asymptote is the leading coefficients. Okay, all right, now we get down into a slant asymptote. They call it an oblique asymptote. I don't like that word for some reason. I just can't remember it, so I call it a slant because that makes more sense to me. Slant asymptote. And that was kind of like on the first page where we had no asymptote here. And I said he kind of looks like a slant. So there's no horizontal asymptote here. There's a vertical one, but there's kind of a slant one that goes through there. Here's how you find the slant asymptote using the equation. Okay. If I would go and do the va and the ha on here, to find the va, I set x minus 2 equal to 0. So x would be equal to 2. Okay. And I go over to 2, and I'm going to put my vertical line up and down at 2. There he is. Okay, but my ha, I look at n and m. N is 2 because it's x to the second power, and m is 1 because it's x to the first power. So n is 2, m is 1, and in my rules, this follows the third rule because n is larger than m, and so there is no horizontal asymptote. None. And now I look for slant. If there's no horizontal asymptote, you always look for a slant asymptote. So if this comes up as none, you look for one of these, and here's how you do this. Slant asymptote, you do long division. unfortunately. Okay, this one actually comes out as kind of decent long division. Here's a review of long division for those of you who forgot. I put x squared, which is the top, I put that on the inside, and I put x, minus 2 on the outside. Okay. Now x squared, I'm going to put plus 0x plus 0 just to fill in behind him. And then I look and I start with my x squared and I say, what do I have to multiply by x to get x squared? Okay, I have to multiply him by an x. So then I take and multiply back through. X times x is x squared, and x times negative 2 is negative 2x. Okay, then I flip the signs, and I go through, and this is 2x plus 0. Okay, one more. I do, what do you have to multiply x by to get 2x, and it's plus 2. So 2 times x is 2x, and 2 times negative 2 is negative 4. Okay, and then I flip my signs, so I get 4, and I have plus 4 over x minus 2. Now, the good part about this long division is that this x, or 4 over x minus 2, we don't care about him. He means nothing to us. To find the slant asymptote, we're only looking at the part in front of the remainder, so x plus 2. My slant asymptote is y equals x plus 2. That x plus 2 comes straight from the long division. Y equals x plus 2. All right, now, for a slant asymptote, y equals x plus 2, this is my equation. To graph that linear function, I start at 2, and I go up 1 over 1, because my slope is 1 over 1. So I start at 2, and I go up 1 over 1, up 1 over 1, up 1 over 1, and this is where my slant asymptote is going to be. Something like this. Okay, and then what's going to happen is for your for the graph of your function, this is still kind of like the first quadrant, and this is still kind of like the third quadrant. Your parabolas, or your hyperbolas, or boomerang things, are going to fit right inside of those pieces, and that's what he will look like. Okay, normally for 1 over x, he's in this corner and this corner, so he's kind of still in those two corners if I would slant that a little bit. So that's what a slant asymptote will do to your function. And there he is. It's the long division, and your slant asymptote is y is equal to this part. You just graph that as a line. So there's that. One more little piece on the back. There's one more funny thing that can happen to your graph, and it's when you have a hole in your graph. Okay, it's called point discontinuity. That is a really big long word. Point discontinuity. Okay. So you see for this linear function, I kind of have a hole right here. It's kind of like where my graph just like drops out, okay? And a scenario when you would have this happen in real life, let's say we are looking at your age and how much money you pay when you're going to like an amusement park or something. Typically, the older that you get, the more money you're going to pay when you go into an amusement park. So maybe when you're 15 years old, you're going to pay $20. When you're 20 years old, you're going to pay $30, and so on and so forth. But let's say it is exactly your birthday. I'm going to put a hole in this graph because you get in for free. So you're going to pay, you're going to pay, you're going to pay, and then as soon as it hits your birthday, you're not going to pay any money because there's going to be a hole in the graph. You get in for free. That's when people lie and say that it's their birthday, right? You know, when it's not actually their birthday. But anyway, that's when this would happen in real life, when you would have like a hole in the graph. Okay, that's one scenario of when it would happen. Okay, and this is very simple. Point discontinuity happens for a graph that looks like this. X squared minus 16, you might recognize that as a difference of two squares. So the square root of x squared is x, and the square root of 16 is 4. So this is x plus 4 and x minus 4. Okay, on the bottom, I've got x minus 4 as well. So those two will actually cancel with each other, and all I'm left with is y equals x plus 4. Okay, well now the graph of y equals x plus 4 is just a linear function. It's x to the first power. So I start at 4, and I go up 1 over 1 because that's my slope. Up 1 over 1, up 1 over 1. So here is my line. This is what my line looks like. Okay, but I have a hole somewhere, and the hole actually has to do with the part that I crossed out. So the part that I crossed out was x minus 4. What I do is I say x minus 4 is equal to 0. Okay, x minus 4 is equal to 0. And then I add 4 to both sides, so x is equal to positive 4. And I go over to positive 4 on the x-axis. Ooh, I should have made my graph go out a little longer. Positive 4 on the x-axis, and I go up to where it hits positive 4 at, and that's where my hole is going to be. Up at positive 4, that's where he is. Okay, so on there, you're just looking at where your graph crosses out, or where your two pieces are the same, where it crosses out, setting that part equal to 0, and that's where your hole is. And what's left over after you cross it out, that's the actual line that you're going to graph. Okay, that's example 4. Graphing rational functions, there's a lot of parts to it. So that was point discontinuity. We've got slant asymptotes, and then we've got vertical asymptotes and horizontal asymptotes. So a lot of rules. You're going to want to make sure you keep this paper handy through the rest of this chapter so you have those rules ready to go.